All right, folks, what we're going to do today in statistics is we are going to take what we learned in the last class, which was how to identify the correlation coefficient, the R, okay, the R correlation. And what we're going to do today is we're going to test the significance of the R correlation. And when I say test the significance of, I mean a hypothesis test. So let's say you have two variables. You have, I don't know, let's say height and weight, or you have education versus income, and you have values from, let's say, 35 different people or 35 different animals or something like that. And you do an R correlation, and you find that the two variables appear to be positively correlated. That doesn't necessarily mean that they are right, get it, positively correlated. It's possible that they might just be accidentally correlated. They may appear as though they're correlated, but in reality, they don't have a correlation at all. And when I say in reality, I mean their populations aren't actually correlated. See, what can happen is you can take any two variables and take a sample of the two variables and then do a correlation analysis between them and find that the correlation is, let's say, R equals 0.375, okay? This looks like what, maybe a weak, close to moderate positive correlation. But the thing is, it's possible that in reality that these two variables are actually not really correlated to each other. So before we get into that, I want to explain a new Greek letter to you. Okay, so let's do that first. Up to this point, we understand that when we're talking about populations and we're talking about samples, right? This is a statistics class, so we're concerned with sample statistics, and we use sample statistics to make inferences about population parameters. And what we have learned so far is that when we're talking about the mean of a sample that we have taken, we're talking about X bar. But when we're talking about the population, the mean of the population, we use the Greek letter mu. You hopefully remember this. When we're talking about the standard deviation of a sample, we use the letter S. But when we're talking about the standard deviation of the population, we use the Greek letter sigma. When we're talking about the variance of a sample, we say S squared, because that's the standard deviation squared. So obviously, when we talk about the population variance, we say sigma squared. But what we just learned about in the last class is the R correlation between two variables, and we use sample data to find the correlation between those two variables, and we call it the R correlation. And so what I want to tell you is that there's a Greek letter that represents the population correlation between two populations. And that letter, I'm going to write it up here in just a minute, but I want to tell you how to pronounce it. It goes R-H-O, all right? And this letter is rho. So say rho, or just say it inside your head, especially if you're wearing headphones and you're at Starbucks. Okay, so rho. The letter I'm about to write up here is the Greek letter rho. But you're not going to think rho. You're going to think a different letter. But I'm telling you that what I write up here is the Greek letter rho. It looks like that. And it looks kind of like a P, right? A Latin P, but it's not a Latin P. It's a Greek letter rho. Okay, so when we're talking about the correlation between two populations, we're talking about the rho value. Now here's what I want to say, is that this R, the sample correlation, will rarely ever actually be 0. So we hardly ever see a situation where when we do a correlation that we get a correlation between two variables that's equal to 0. Because in the real world, there's always some kind of error. There's always some sort of happenstance or some sort of accident that basically causes two variables to appear as though they are correlated to each other. But when we go over to the population, when we think of the letter rho, we can say, if we look at the population of one variable and the population of a second variable, if theoretically these two variables are completely unrelated to each other, then theoretically what we're saying is that the rho value is 0. Why? Because we're saying the correlation is 0. When two things have a 0 correlation, that means that they're not related to each other at all in any way. Okay, so this is important. I want you to understand this. The main thing I want you to understand about it is any time that we say that rho is equal to 0, we're saying that the two variables are not correlated to each other at all. Okay? All right, so now we're going to do a problem where I actually show you how to test the significance of the R correlation. All right, in order to test this significance of the R correlation, or in order for me to teach you how to test the significance of the R correlation, we're going to use a data set. And so you can see this data over here. And what I'm going to do is I'm about to put this up so it's bigger on your screen so that you can enter it. When I sort of blow this up so that you can see it better, make sure that you either write it all down or make sure you type it all into Excel. Okay? So right now I'm going to go ahead and put that up so you can see it easier. Okay, so what we're going to do is we're going to use that data, and you can see it doesn't matter what these variables are. You can see that it says cart and felt. It doesn't matter what cart means. It doesn't matter what felt means. A lot of times when you're doing research, you'll come up with these abbreviations for all these variables that you're dealing with. But we're trying to identify, is there a correlation between the variable cart and the variable felt? And if there is a correlation, is that correlation significant? And what I'm going to do is in just a minute is I'm going to put the procedure up here on how to test it. Okay, so here's our question. We want to test whether the correlation between the variable cart and the variable felt is not 0 at the alpha equals 0.05 level of significance. Now, before I get into the procedure on how to do this, it's important that you understand that we can actually do 3 different kinds of tests. When we're doing this, we can do a two-tail test, and that's what's happening here. And two-tail is when you're testing whether the correlation is not 0. Or you can do a left tail test, and a left tail test is when you're testing whether the correlation is negative. Is it less than 0? That's where you'll be asked, well, test whether there is a negative correlation between these two variables. Similarly, you can test whether the correlation is a positive correlation, and that would be a right tail test. One more thing I want to tell you is that so far in this class, you have learned about 3 different kinds of tests. You've learned about z-tests, t-tests, and f-tests. And each one of them has its own table where you find your critical values. What I want you to know is that when you're doing one of these tests, this correlation test is a t-test. So you're going to need to go get your t-table so that you can identify the critical values to be able to do this hypothesis test. All right, what I'm going to do now is I'm going to go through the steps. I'm going to go through the procedure that you need to follow to be able to identify whether the R is significant, whether the correlation, to test whether the correlation between these two variables is significant or not. Well, step 1, the very first thing you want to do is you want to identify the R correlation, okay? So you want to go into Excel, or maybe you're using SPSS, or you're using a TI-84 calculator, however it is that you're going to go in and identify the R correlation. Now, bear in mind, I taught you how to do this in the last class, okay? So you should be able to go in and do exactly what you did in the previous class and enter the data from the two columns and find the correlation between the two variables. Okay? Once you have the R correlation, then what you're going to do is you're going to state your null and alternative hypotheses. Okay? So in this case, we're going to say that we have the null hypothesis and we have the alternative hypothesis. Now, the alternative hypothesis is always what it is that you're testing. And in this particular question, we're testing whether the correlation is not 0. So the null hypothesis is always the basic assumption when we don't have any data. And typically what we do is we automatically assume that two variables are not correlated to each other in any way. Until we have scientific data that shows us that two variables are correlated to each other, we assume that they are not correlated to each other. Okay? So the null hypothesis is that the correlation is 0. Remember, when rho is equal to 0, when the correlation is 0, that means no relationship. That means 0 relationship. What's your relationship? Is an example. Hey, John, what's your relationship to Mary? We have 0 relationship. Oh, that must mean you have no relationship at all. That's correct. If the correlation is 0, that means no relationship. So then the alternative hypothesis is that there is a relationship. That means that the correlation is not 0. It could be positive, it could be negative, but it's some kind of relationship. Okay? So that's our null and alternative hypotheses. Then we're going to state whether it's a two-tail test, a right-tail test, or a left-tail test. When it's not 0, this is a two-tail test. Two-tail test. Next step. We're going to identify our alpha. In this particular case, we were told to test at the 0.05 level of significance, and we need the p-value. And the p-value, if it's a two-tail test, well, we always divide our alpha by 2. So in this case, our p is 0.025. Okay? Step 4, we are going to identify the kind of test, and this is a t-test. And when it's a t-test, we also have to identify the degrees of freedom. All right, so in this, in a correlation test, when you're testing the significance of the correlation between two variables, because there are two variables, your degrees of freedom are going to be n minus 2. Because your degrees of freedom are always n minus the number of variables that you're dealing with, two variables. Oops, I just wrote an n minus 1. And you also want to identify the degrees of freedom because it's a t-test. So when we go to the t-table, there's the degrees of freedom along the side, so we got to know what the degrees of freedom are. Well, in a two-variable test, because we have two variables here, we have cart and we have felt, the degrees of freedom are going to be n minus 2. So degrees of freedom, n minus 2. Okay? In this particular case, if you look at the variable, if you got to count up how many variables there are, and I believe that there are 15, or not variables, there's two variables, you got to count up how many samples there are. How many entries are there with the two variables? And if you go down the line, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 lines for cart and felt, and therefore 15 minus 2, in this case, degrees of freedom is 13. Okay? So we've got a p of 0.025 and degrees of freedom 13. Okay? All right. Step 5. The next thing we're going to do is we are going to identify the critical t value. All right. Now, for the critical t value, if it's a two-tail test, it's going to be plus or minus. If it's a left-tail test, it's going to be minus. And if it's a right-tail test, it's going to be positive. And that's because, remember, with the curve here, with the distribution curve, a two-tail test is on the left side and the right side. It's two tails. This is the negative tail, and this is the positive tail. So it's plus or minus. If it's just a right-tail test over here, then it's just positive. If it's just a left-tail test, then it's just negative. In this case, it's a two-tail test. Therefore, our critical t value is going to be plus or minus. Now we need to go to the t-table. You get a t-table here. We're looking up degrees of freedom is 13. So along the side, we're going to go to 13. The p-value is 0.025. So along the top, we're going to go over to 0.025, and go down to degrees of freedom 13, and I see 2.160. So 2.160. Okay? Now, I just realized that we forgot to identify the R correlation. We've been doing all these things, but step one said identify the R correlation. So let's go ahead and do the R correlation real quick, okay? All right, I'm going to turn this on. And there's our data. And if you recall, the way we do an R correlation is we go to data, then we go to data analysis, we select correlation, which is right here. We hit OK. Then under input range, we select both columns of data, okay? Then press enter. And then they're in columns. We're going to go down here to output range. And let's say we put it maybe right here. And we'll press enter and then hit OK. And here's our correlation right here. And I'll zoom in on that. And you can see that our correlation is 0.56, and we round to the third decimal place. Our R correlation is 0.561. Okay? So we've got our R correlation here. All right, so here, R equals 0.561. Now, the last thing, oh, and then we have to do our, along with step 5, our critical t-value, we also want to make our decision rule. And our decision rule is going to be reject the null hypothesis if t is less than negative 2.160 or if t is greater than positive 2.160. And now, the last thing we need is we need to know how to calculate the t statistic. Okay, this one's sort of crazy. So write this one down in your notes. You're going to want to remember this one. The formula for the t is you put r in the numerator, and then in the denominator, you're going to do a big square root. And in that big square root, you're going to have a fraction. And in the numerator, that fraction is 1 minus r squared. And then the denominator is n minus 2. Basically, that means your degrees of freedom are in the denominator. And the R correlation, that goes up here. And you can also put the R correlation, 0.561, you can put it right here, and then you're going to square it. So step 6 is to calculate the t statistic and make a decision. So in this case, we can calculate our t statistic. What is R? R is 0.561. So we're going to put 0.561 divided by the square root of 1 minus, and in parentheses, I'm going to put 0.561, close the parentheses, then square, divided by n minus 2. Well, that's the degrees of freedom, which is 13. So I'm going to put 13 down here. Now, when I do this in the calculator, I'm also going to put parentheses around the 1 and the square. And so now, it's going to be sort of complicated how I enter this in the calculator. So watch, let me show you what I'm going to key in when I key it in the calculator. Let me write it over here. I'm going to key in 0.561. Then I'm going to hit the divided button. Then do you see this big square root here? I'm going to key in square root. All right, now usually in my scientific calculator, when I hit the square root button, this is what it gives me. It gives me a radical symbol with a parenthesis. Now, that parenthesis is not this parenthesis. It's the parenthesis for the radical. So now to key in 1 minus 0.561 squared, I'm going to have to open another parenthesis and do 1 minus. Then I'm going to open another parenthesis and put 0.561, close this parenthesis and square it. And when I square, sometimes your scientific calculator, it'll have this symbol to the power of 2. Then I'm going to close that parenthesis and then divided by 13. Divided by 13. Then I can close the parenthesis on the radical and press enter. Okay? You're probably going to have to practice with this a lot to make sure that you can get the right number. But let me grab a calculator. And so here's what I'm doing. I'm going to do 0.561 divided by radical. Okay, I'm going to hit the square root of, and it opened a parenthesis just like I said it would. Then I want to put parenthesis 1 minus. So a new parenthesis, 1 minus, then a parenthesis for open parenthesis 0.561, close parenthesis, and then I've got a squared button. So I'm going to hit the squared button. Then I'm going to close the parenthesis on the 1 minus 0.561 squared. Then divide by 13. Then I'm going to close the overall radical parentheses. And I press enter. And I get, in this case, I get 2.443. 2.443. So the question is, if t is 2.443, is that less than negative 2.160, or is it larger than 2.160? Yes, it is larger. 2.443 is larger than 2.160. Therefore, we will reject the null hypothesis. So I'm going to say reject H sub O, and that means that this correlation, R.56 is equal to 0.561, what we're saying is that it is a significant correlation. These two variables, this data supports the claim that these two variables are related to each other. Now, this is just one correlation. This is one sample. It's possible that some other person who's investigating these same two variables may come back and say, no, they're not related to each other at all. We did the same correlation analysis. We were not able to replicate this. And when they can't replicate your research, that means that there's reason to believe that it may not be accurate. Okay? All right, let's do another example, okay? All right, here's another set of data here. And the question says, conduct a test at the alpha equals 0.02 significance level to determine if the variable Yeti and the variable NIWR are negatively correlated. So this isn't asking if the correlation is not zero. It's asking specifically if the correlation is negative. This is going to be a one-tail test, and it's going to be a left-tail test. Now what I'm going to do is I'm going to go ahead and blow up those variables right there so that you can see them better, so that you can key them into Excel. All right, so now that you've keyed them, hopefully by now you've keyed them into Excel, and the very first thing we need to do is we need to identify the R correlation between these two variables. So let me go over to my computer here, and I will put the correlation maybe right here. So we'll go data analysis, correlation, okay. For the input variables, we're going to go down here, select these two variables that we're dealing with. Press enter, and we're going to make the output range. Let's see here. The output range, let's say right here. Press enter, and there it is. Here's our correlation. I'm going to zoom in on that, and you can see that the correlation is negative 0.252. So R equals negative 0.252. All right, that's all we need from the computer, so I'm going to go ahead and turn off the projector, and now we can do the rest of this problem, now that we have the correlation. All right, so we identified the R correlation, and now we want to do the null and alternative hypothesis. Well, what we're testing, our alternative hypothesis, is that the correlation is negative. So that's going to be rho is less than 0. So that makes our null hypothesis, rho is greater than or equal to 0. Remember, our null hypothesis is always all of the opposite of whatever our alternative hypothesis is. Okay? So we've got our null hypothesis, our alternative hypothesis. This, because we're testing whether rho is less than 0. Well, what's less than 0? Negative things are on the left-hand side. So that makes this a left tail test. Left tail test. At the alpha equals 0.02 level of significance, and because it's a one-tail test, a one-tail t-test, that means that our p-value is the same as our alpha. So that's p is 0.02. What kind of test is it? It's a t-test. And we need degrees of freedom. And let me remind you that in this case, degrees of freedom is equal to n minus 2. Well, I forgot to count how many observations there were. So let's go over here. Let me go to the computer, and it looks to me like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It looks like 18 observations. And because there are 18 observations, 18 minus 2 is 16. So our degrees of freedom are 16. Our p is 0.02. So now we can go to our t table and find our critical t value. So t crit. Now, is our critical t value going to be positive or is it going to be negative? Well, this is a left tail test. What is on the left side of 0? Well, that's less than 0, okay? So then on the left side are all the negative t values. So let's go to 0.025, go down to degrees of freedom of 16. I'm seeing 2.120, but it's going to be negative 2.120 because all left tail tests have a negative critical t value. So now our decision rule is going to be to reject the null hypothesis if our t statistic is less than negative 2.120. Okay? You've done a lot of these hypothesis tests up till now. You get it. You understand. And so now the only thing we need is to calculate our t statistic. Okay, and what is our formula for the t statistic? It's r over big square root of 1 minus r squared over n minus 2, which is basically the degrees of freedom. Well, it is the degrees of freedom. So our r correlation is negative 0.252 divided by big square root 1 minus, now I'm going to put the negative 0.252 in parentheses and then square it. Now the reason I'm putting it in parentheses is because when I square a negative, it's got to be the negative times the negative. Okay, so I got to put it inside of parentheses. Otherwise, when I put it in the calculator, it'll actually give me a negative value for my r squared, and that's inappropriate. A negative times a negative is a positive. R squares are always positive. Degrees of freedom in this case are 16. So now all I have to do is key this whole thing into the calculator. So let me grab a calculator. Here's what I'm going to key in. Negative 0.252. Negative 0.252 divided by square root of. Now, I'm going to go parenthesis 1 minus, open a parenthesis, and put in negative 0.252. Close the parenthesis, squared. Then I'm going to close a parenthesis here so that the whole numerator, see what I'm basically doing is I'm putting the entire numerator in parentheses. Why are you doing that, Mr. Ryan? Because there's a minus. There's a subtraction in the numerator. And what a lot of students do, they mess up because they don't put the numerator in parentheses. They just key in 1 minus this value squared divided by 16. And what the calculator would do then is it would divide this by 16 first. Then it would subtract it from 1. That's why I'm putting parentheses. Now, if you want to do all these numbers separately and then pile them all together, that's fine. But if you do it that way, you be careful about rounding. You're going to want to go out to like 6 or 7 decimal places because you don't want to round, get the wrong answer, because I'm going to ask you to give me the answer to 3 decimal places. So if you're giving me an answer to 3 decimal places, you may want to go out to 5 or 6 decimal places. Okay? All right, so now divided by 16. and then I'm going to close off the parenthesis for the whole radical. I'm going to press enter, and I get negative 1.042. Rounded, that's rounded. Negative 1.042. So my t statistic is negative 1.042, which is not smaller than negative 2.120, and therefore I say do not reject. My decision is do not reject H sub O. Do not reject H sub O. Okay? And that is our second example. Let's do one more example. All right, let's do this last example here. We've got some data there. We got variables VEAX and KTYH. It says conduct a test at the alpha equals 0.01 significance level to determine if VEAX and KTYH are positively correlated. So now, since it's asking specifically whether the two variables are positively correlated, it's going to be a one-tail test and it's going to be a right tail test because we're only looking for a positive correlation. Okay? So the first thing that we're going to need is you need to see this data. So I'm going to blow this data up and then put it up on the so that you can see it closer, and then you can put it in Excel. Okay, so now, hopefully you put all that data in Excel, and now we can do our first thing, which is identify the R correlation between those two variables. So I'm going over to my computer here. I'm going to select Data Analysis, Correlation, and then I'm going to select, let's clear these out. I'm going to select down here, there they are. I'm going to select all these variables. It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like there are 11 observations. Press enter. And then output range, we'll put it right about here. Okay. And we'll hit OK. And there it looks like the correlation is 0.705, rounded to 3 decimal places. So our R correlation is 0.705. Okay? Now we're going to test whether that correlation is significant or not. So let's go ahead and turn this off. All right, so positive correlation, alpha is 0.01. We've got our R correlation. Now we're going to do our hypotheses. Well, our null hypothesis and our alternative hypothesis. The alternative hypothesis is we're testing whether the correlation, which is rho, population correlation is rho, whether it is positive. So that's positive means greater than 0, which means our null hypothesis would be the opposite of that, which would be less than or equal to 0. So the correlation is either negative or it's equal to 0, either no relationship at all or a negative relationship, because what we're testing is whether it's a positive relationship. This is a one-tail test, specifically a right tail test. So we're doing a right tail test. Let's see here. Now we want to identify the alpha and the p-value. Well, the alpha given in the problem is 0.01, and because it's a one-tail test and it's a t-test, our p-value is going to be the same as our alpha. So the p-value that we're going to look up in the table is 0.01. This is a t-test. So we're going to go t-test, and the degrees of freedom are going to be n minus 2. Remember, we counted the observations when we identified the correlation, and there were 11 observations. 11 minus 2 is 9. So the degrees of freedom for this problem are 9. Degrees of freedom 9, p is 0.01. So let's go to the 0.01 column in our t-chart. Let's go down to degrees of freedom 9, and I see 2.821. 2.821. So the critical t-value is 2.821, and it's positive. Why is it positive? Because we're doing a right tail test. And so our decision rule is going to be to reject the null hypothesis if our calculated t-value is greater than 2.821. Okay? So now we have a decision rule, we have a critical t-value. The only thing we need now is a t-statistic. So we know that the way we calculate it is we do the r divided by big square root of 1 minus r squared divided by n minus 2. So now what you could do is, if you wanted to, you could calculate this r squared first, but that could give you a rounding problem. So be careful about doing that. But here we're going to key in here is our r is 0.705 divided by big square root 1 minus 0.705 squared over n minus 2, in this case, degrees of freedom, is 9. So let's get a calculator. Here we go. And we'll do 0.705 divided by square root, big square root. Okay, I'm going to do parenthesis 1 minus 0.705 squared. Now, I don't have to put parentheses around the 0.705 here because it's not negative, but you could still put it there. Then I'm going to close off this parenthesis and divide by 9. Then I'm going to close off the parenthesis for the radical, press enter, and I get 2.982. 2.982. So our t statistic is 2.982. And 2.982 is larger than 2.821. Therefore, we will reject the null hypothesis. Reject H sub O. And what that means is this is statistical evidence to indicate that there is a positive correlation between these two variables. Okay? So hopefully these examples have helped you, and hopefully you'll have an understanding of testing the significance of the R correlation. The next thing we're going to learn is called linear regression. And when we do linear regression, it's related to this R correlation a little bit. And so you're going to want to, sometimes when we do linear regression, we will also, in addition to doing the linear regression, we will test the significance of R. So be ready to do this again, okay?